So welcome to lecture 12 of MCS 471 on numerical analysis, or in particular on here in this sequence on numerical linear algebra. So the matrices or the linear systems that are occurring in practical applications are mostly special. So in this lecture, we will consider symmetric, positive, semi-definite matrices. So actually, these are matrices that are very particular, but as we will see, or they will actually arise in the context of optimization, a very important field. For symmetric, positive, semi-definite matrices, we do have Cholesky factorization. We will, in the main part of this lecture, we will derive the formulas, and then we will see a variation of this. So there is the L times L transpose factorization that will require square root. If you are a little bit uncomfortable about the square root, there is an L times D times L transpose factorization that does not require the square root. And as typical in this course, our algorithms are defined as Julia functions. So in the third part of this lecture, we look into the costs. So why actually do this, essentially? Well, we do this because a Cholesky factorization can be computed twice as fast as an LU factorization. So we will provide an accurate count that will actually demonstrate that the cost of a Cholesky factorization is half of the cost of an LU factorization. When we discussed the LU factorization, we pointed out that the cost was cubic. We did not provide a very rigorous count because it was obvious that by the triple nested for loop that we had a cubic cost algorithm. Here it matters actually what the constant is. So in this course, it's not only the asymptotic order that matters, but also actually the constant in front of the leading in front of the leading term. And as we will see at the very end, when we time Julia functions on very large matrices, we will see that Cholesky actually is faster, noticeably faster than the LU factorization. All right, so let's dive in then. So we will solve structured linear systems. And the first type of structure occurs when the matrix is symmetric. So formally, we say that a matrix is symmetric if its transpose leaves the matrix invariant. So here is an example. So the diagonal of this matrix A here consists of the elements at position 1, 1, position 2, position 3, 3. So what you do is actually you consider that diagonal again. That doesn't change. But then you see that the element 1 here on the third row, first column, becomes now in the third column, first row. So the 1 gets flipped across the diagonal. So that's the transpose. You could also say that the rows become the columns and the columns become the rows. So if we compute now an LU factorization, then actually of a symmetric matrix, then actually the upper triangular part will be the transpose of the lower triangular part. So in a way, symmetric matrices would be very good test matrices on the correctness of your LU factorization. So symmetry occurs almost everywhere, and it's very important to be able to deal with this. The other the other important structure element are given by matrices that are positive semi-definite. So to every matrix, you can actually make a quadratic form. So this is actually a quadratic form, which is a function in x. So you do A times x, and you do x transpose of that matrix vector product. That gives a quadratic form. We say that the matrix is positive semi-definite if for all the vectors that you can make, also the negative ones, also ones with negative coordinates, that the result of this quadratic form is positive or eventually zero. So this is a positive semi-definite matrix. A positive definite matrix, then the inequality is replaced by a strict equality. So here is a very simple example. So you notice that this matrix is symmetric. And if we do this product, so of a variable vector x, then we arrive at a quadratic form. And actually also that quadratic form is actually symmetric. If you flip x1 with x2, then that actually leaves the form invariant. Why is this positive? Well, we could try to prove this analytically, but actually a picture makes the proof here. So if we make a three-dimensional plot, then you can see that I picked one camera point of view that probably makes it more or less obvious. So you definitely see that if you go in certain directions, that the value of the height of the surface will actually rise faster than in other directions. But the point is that the positive semi-definite matrix corresponds to a surface where there is a unique minimum. So positive semi-definite matrices occur very often with in the context of minimization. All right. I spoke about the directions in which you can go. So if you look at any direction, then some directions are more special than others. The very special directions are the eigenvectors. So every matrix has an eigenvalue and eigenvector pair. Actually, any matrix of dimension n has n eigenvalues, eigenvector pairs in general. And what is an eigenvalue eigenvector pair? Well, if you multiply the matrix with the eigenvector, then you obtain a multiple of this eigenvector. Let's do this. So here for this simple matrix, I have the eigenvalue 1 and the vector v. Now, if you do the matrix vector multiplication, then you end up with the same vector again. So this vector, actually, you can multiply the matrix as many times as you like, but you always have the same vector again. So again, symmetry. So the eigenvectors with eigenvalue 1, if you now look at the matrix as a linear map, then those eigenvectors with eigenvalue 1 actually are invariant, so for the matrix vector multiplication. So symmetry again. Okay, how does this now fit? Well, we can relate the eigenvalues of the matrix, in particular the theorem says it here, if all eigenvalues are non-negative, so they are positive or zero, then the matrix itself is positive semi-definite. And we will prove this theorem in general not in general, but for a 2 by 2 matrix. So if you can do this for a 2 by 2, then you can do this for any matrix. So if we have, so in here it's still quite in general, but not actually in complete generality. So we assume actually that the eigenvectors and the eigenvalues are all distinct from each other. So we talked in the root finding problem about multiple roots. If you with the eigenvalues, there is also eigenvalues are the roots of a polynomial, and they can also be multiple. If you took a linear algebra course, you may have seen the characteristic polynomial of a matrix. So here we are in the case where we assume, for the example of a 2 by 2, that we have two distinct eigenvectors. We call them V and W, and the eigenvalues are lambda and mu. Now we are in a two-dimensional space, and since the eigenvectors are distinct from each other, they form a basis. So any vector x you can write as a linear combination of these two eigenvectors. Now, we assuming that the eigenvalues lambda and mu are non-negative. And we will now check that the matrix, when we look at the quadratic form defined by the matrix, that quadratic form is also non-negative. So we do the matrix vector multiplication. So it's a linear map. So if we do the product of A with a linear combination, then we get a linear combination of the results of the linear map. And also the inner product is actually also a linear map. So we apply the linearity twice. So, and then we have the quadratic form where whatever the coordinates of the eigenvectors are, we just square them. So all the numbers here of these two inner product, they are positive numbers. The alpha and the beta, it depends on the value of x, but we square them, so also positive numbers. Fine, so the only two numbers that do not appear as squares are the lambda and the mu, and they are non-negative. The entire expression is thus non-negative. So if we have eigenvalues of our matrix and we know that they're all non-negative, then we have a positive semi-definite matrix. So that is, by the way, one way to make a positive semi-definite matrix. Okay, so let's look how we can do that. So we will check our simple example matrix in Julia. So we enter the matrix as a list and reshape it into a 2 by 2 matrix. Then computing the eigenvalues, we find the eigenvalue 1, so as in the example, and then we have the eigenvalue 3. So the matrix, that very simple matrix, has two nice eigenvalues. It's also a nice matrix, so the spectral radius, the largest eigenvalue in absolute value, is 3 here. So that's another way to compute the norm of the matrix via the eigenvalue decomposition. So now, what is the eigenvalue decomposition in full? So let's first verify. We can compute also the matrix of the eigenvectors. So remember the minus square root of divided by 2. So that's actually the first column here. So the first column of this matrix is the first eigenvector with the eigenvalue 1, and the second eigenvector, the second column, is the vector of the V, the second column is actually the second eigenvector. So if we do the matrix vector multiplication, then you see that the first column of the product is the same, but the second column has changed. Now we can verify that the second column is 3 times the second eigenvalue, or second column of that matrix V. So we have the property of an eigenvalue-eigenvector pair. If you multiply the matrix with an eigenvector, you get a multiple of the eigenvector back. You can see this for all the eigenvectors and see this as a matrix product. So the A times V here, I should have used capital V. The A times V here is a matrix product. This is a scalar multiplication. So, and we can use that property to actually do the decomposition. Perhaps let me back up a little bit. So I have that A times V equals actually a diagonal matrix. So typically this is called lambda times V. And this actually gives another decomposition of the matrix A. So the matrix V is invertible, and we actually can make the spectral decomposition of the matrix. So we have the inverse of V. We have the matrix of where a diagonal matrix. So instead of lambda, I'm using here now the big lambda. So this is the capital lambda, which is a diagonal matrix. And then I have the matrix of the eigenvectors. So how can you make a positive definite matrix? Well, you generate an orthogonal matrix. So you take the transpose of the orthogonal matrix, because orthogonal matrix, the inverse is again, so the orthogonal matrix, the transpose is actually its inverse. So if you make this product, this will give you a random positive definite matrix, where D has only positive elements on its diagonal. So this decomposition of the matrix A is actually called its spectral decomposition. So that's kind of a detour. So you can verify, so I omitted this on the slides here, but the slides could actually still have continued. So if you had the diagonal matrix with the eigenvalues, then actually you can verify this property. So this property here is only verified for the second column. All right, but let's not digress too much. We still have a lot to cover. So let's look now at the Cholesky factorization. So if the matrix is symmetric and positive semi-definite, then we can compute the LU decomposition twice as fast. And actually what we compute is the Cholesky factorization. The Cholesky factorization is a factorization in a lower triangular and an upper triangular part. But you only have to compute the lower triangular part. So, and we will prove that rigorously, although you can already see it from that any good algorithm will actually take advantage of this, that you will only have half as many operations compared to the LU. So the other issue is that no pivoting is needed because the A is actually positive semi-definite. We will not go over this, but the algorithm that we will see is a numerically stable algorithm. The key in this is that if you take a submatrix of a positive definite matrix, then that submatrix is also positive semi-definite. And that's not too hard to see. So you actually omit the first column, the first row, you have a submatrix. Now, if you look again at the quadratic form, what it means is that you knock off certain terms. But if what you had was already positive semi-definite, so all the terms are actually positive as well. So I will not go in there as much. So read the textbook for this. All right, how do we now make a positive semi-definite matrices? We could use the spectral decomposition, but we will actually use the lower, actually an easier way, if you like. We can take a random 2x2 matrix and multiply that the lower triangular part with the upper triangular part, with the transpose. So that actually gives us then the LU factorization. So that's working backwards. So what we will do is we have here, you see a symmetric matrix. So actually the elements on the off diagonal are the same. So that's how you see it. So we want to compute the LU decomposition or the Cholesky factorization, but we know it already. So in a way, this is a better way than working with what I first indicated as a spectral decomposition. So we can immediately verify that the matrices that we construct are actually positive, definite. So by the way, what does it mean in eigenvalue 0? It actually means that the matrix is singular. So that's another thing. So if you have a 0 matrix, then multiplying, if you have a 0 eigenvalue, multiplying with the corresponding eigenvector will actually make everything 0, will return the 0 vector. So the eigenvector corresponding to the eigenvalue 0 is actually then a vector that is a 0 of the linear map. So, and if you think about what is a matrix vector multiplication, it's actually making a combination of the columns. And if you have a linear combination of the columns that equals 0, that is a singular matrix. So in general, we talk about semi-definite matrices, but actually for all practical purposes, we want positive definite matrices. So they should be positive. This one is already a bit smaller than the other. All right, so we continue our verification here. So we can try we have a quadratic form, and what we here do is we try to evaluate the quadratic form at a negative matrix. So at a vector where we see that the first component is actually the larger component. So let's make it negative. So let's go in the negative direction. But even if you go in that more negative direction, you have still a 0. You still have a positive number. So this quadratic form will be everywhere positive. So I should have made a picture here. So this is just a sample, a random vector. Include some negatives and see whether your quadratic form might give up. So this is kind of a statistical sample to verify whether your matrix could be not positive semi-definite. The plot will actually, for this case here, provide a much better solution. All right, so let us now go into the main part of the lecture, the derivation of the formulas and the algorithm and the Julia function of the Cholesky factorization. So we start with the formulas. So at the left, so we have a matrix product. At the left, we have the known coefficients, the given coefficients. And you see that they are symmetric. So I have used the A21. So for the second row, first column, and also at the first row, second column, I'm using the same indices. So normally you would not do this indexing. You would put a 1, 2 here. But the matrix is actually symmetric. And I give a preference for the first index because we are computing the lower triangular part. So we have given, so as an equation, at the left we have 6 known numbers, and at the right we have 6 unknown, 3 on the diagonal, 3 off the diagonal. So we can proceed column-wise, and here for this 3 by 3 example, everything fits on one slide. So we compute the first column first by identifying the first column of our product with the first column of the given coefficients. And then we solve for the unknown L factors. So you see that if we go in the right order, first element first, then we know the L11, and we can use it to compute the L2,1 and the L3,1. We need a square root. Now, the square root of negative numbers will give complex numbers. We will not have complex numbers because our matrix is positive semi-definite. So that's the first column. So the second column is then solved similarly. So we actually start from the diagonal. So the diagonal gives us, we solve for L22. So we know already L2, 1. Computed that already. We also know the A2, 2. That's the given. Then we continue. Here again we see the square root coming in. And then you see the formulas that are very similar to the solving of the triangular systems. So we eliminate, essentially, subtract from the given coefficient the product of the known elements on the lower triangular matrix. And again, we can divide by the L22 because our matrix is positive definite. So actually, I said in the previous time, for L11, it suffices that the matrix is positive semi-definite. But if the matrix has somewhere a 0 eigenvalue, then the division will not work out. So we actually do require positive definite matrices. So all the diagonal elements will not be 0. And then for the third element, we compute again a square root. So let's look at an example. So if you had to do this by hand, so perhaps this example might be a little bit clearing up things, or perhaps not. So this is a nice example where you can compute everything by hand. And these numbers are very nice. So I constructed this example by working from the bottom L and doing the matrix multiplication of L with its transpose. So in a way, computing the the Cholesky factorization is working backwards. Okay, so the formulas that we derived essentially for the 3 by 3 case can be generalized. So if you, perhaps this is a little bit going too fast, but if you have doubts on this, please work this out for a 4 by 4. And then you will see the general patterns coming in. So we have two different formulas. We have formulas for the diagonal elements. So the 1/2 here is the square root. So for the first element, we just computed one square root. For the second element, we subtracted the square, and it went on like this. So then for the other elements, we have the division here, and we do the elimination essentially. So we subtract from the given coefficient, we subtract the products. So these formulas are very similar to what we did with the LU factorization. Except now you can actually see that we have the transpose. So in the matrix multiplication, you have the index k that runs over the columns of the first matrix. So k is here second. And then the k would be first in the second matrix. But since the second matrix here is the transpose, we actually have flipped these two indices. So instead of having k comma j, we have j comma k. So that indicates that we actually are in the unraveling of the L times L transpose product. We actually are kind of recomputing these products, but then in a very organized manner. So you can see the loop structure here. So this is a for loop. It's actually a double for loop. So the I runs from 1 to n, runs over all the columns. The j runs here now over, the j actually runs over all the columns. The I runs over all the rows. So the j is actually the outer loop. So we have two explicit loops, the I and the j. Then we have the loop in the big sigma. So this algorithm will still have a cubic cost. So we will use these formulas to provide very accurate cost counts. But already here you can see it is cubic. All right, in transitioning to the Julia code, we give the pseudocode. So now actually what this means is that the big sigma is written out very explicitly. So the big sigma that we had on the previous slide is written out. There was also a sigma in the diagonal formula. So the big sigmas are translated explicitly into for loops. This is an in-place algorithm. You see that we are not working with the else anymore. The else have disappeared. We can simply replace the elements in the matrix. So the algorithm can be very space efficient. So at the very end of this lecture, we will work with a lot larger matrices than 3 by 3 and 2 by 2. So that actually matters. That's another property of the Cholesky factorization. That's the same property that the LU factorization have. So these algorithms can be implemented as an in-place. So the amount of storage is actually the same as the input. All right. For completeness, so in a way, this illustrates how nice the algorithm is. So the formulas fit into a correct Julia function. So I call it our Cholesky because there is a Cholesky in the linear algebra module of Julia. So I had a name conflict when I first tried to define the function Cholesky. So the formulas, as in the pseudocode, are actually the same as the formulas in the Julia code. So there's very little difference. All right then, time for some exercises now. One can, for any symmetric positive semidefinite matrix, derive the LDL transpose decomposition. If the square root function would make you uncomfortable somehow, you can eliminate the square root. So in a way, this is the purpose of this exercise. Derive the formulas for a square root free Cholesky-like factorization. And you can do this explicitly just by working out the matrix products. It looks a little bit more complicated, but at the left you will have of the matrix equation, at the left you have 6 known numbers, at the right you have 6 unknown numbers. You have the formulas for the diagonal and then the formulas for the off diagonal for the lower triangular part. So derive the formulas. So the next 2 exercises are following from that. If you have the correct formulas, and SymPy might actually help you here. So if you are a little bit doubtful, work it out in SymPy. And the advantage of SymPy is that you can, once you have the formulas for the 6 known elements, you can actually make all the products and verify with the expand and the simplify that actually when you do the multiplication, the variables that you have picked for the L and the D's will actually cancel out. It will be simplified out and you will have your simplification. So in a way, this is a very nice symbolic computation. We are actually after Julia functions, so work this out for into a Julia program, the formulas, and demonstrate the correctness on some random 4x4 matrices. Or you can also compare, well, you cannot compare with Cholesky. So that's the goal for the exercises 2 and 3. An alternative to the Cholesky. All right, Julia has a built-in LU factorization. So we can start from an upper triangular matrix if we can do this different now. So the Cholesky factorization in Julia will actually return the upper triangular matrix. So that's kind of a nice, kind of an oddity. Just if you are suspicious of this, you can actually reformulate our Cholesky now that it is an upper triangular formulation. We can compare to our Cholesky, and we see that on the same matrix that our Cholesky returns exactly the same matrix as the Cholesky of the linear algebra module. All right, so now I have about 10 minutes left, and that should be sufficient to explain the third part of this lecture. So the Cholesky factorization is a simpler algorithm than the LU factorization. So that could already be a benefit to using the Cholesky factorization. No row pivoting that is necessary. And by the way, so if the Cholesky factorization breaks down, that could actually also be an indication that your matrix is not positive definite. What we will do in this last part is verifying very precisely the cost of the Cholesky factorization. For the LU factorization, we did not derive an explicit formula because then it was sufficient that we understood that this is cubic in the dimension. Now the constant actually matters, and therefore it's worthwhile to actually explicitly count the number of floating point operations that we are doing. So we have derived the formula for the diagonal elements. So let's examine that formula. So what we do is we have the big sigma sitting in there. So that's the inner for loop. So the big sigma here is executed I minus 1 times, and we have this first subtraction here. So inside we have I minus 1 terms, and we will actually do one more subtraction. So we have I subtractions. Then we do I minus 1 multiplications, and we have 1 square root. So that's the inner sigma. So what is for one diagonal element? We have n diagonal elements. So we will do that many operations. All right, that gives us the statement of the lemma. The lemma says that it requires n squared plus n floating point operations to compute all diagonal elements in the Cholesky factorization. All right. I should note out now that if you really paid very close attention, then you can say that we had I minus 1 subtractions. And this will complicate the notation only a little bit. So you have then n squared minus n. But the n square is most important. We apply the same reasoning now to the lower diagonal elements. And now we get to a little bit more complicated reasoning. So we start from the formula again. So we look at the formula for one lower diagonal element, and we have the big sigma that we say will require j minus 1 operations to do. So I see the big sigma essentially as a function of as many arguments as its length. So here we have j minus 1 steps. So in some sense, doing this as the sum functions, we do have j minus 1 operations. And we have one extra subtraction here. So we have j subtractions. In the sum, you could say, do you do additions? But these are all floating point operations. So we have j minus 1 multiplications inside the big sigma, and we do one division. So this all adds up again to 2 times j operations. So for the ijth element. Then we execute the 2 for loops. So the innermost for loop runs over the j, and then the outermost for loop runs over the rows. The reasoning is a little bit more complicated because we have this big sigma sitting here. So I would expect that you know this formula, but this formula also here I had to look up. And this is where the cubic comes in. So the explicit formula for the sum of the squares gives actually the n to the power 3 divided by 3. And that gives then the conclusion of the lemma, of the second lemma, that the computation of all lower diagonal elements has a cost of n to the power 3 divided by 3 minus n divided by 3. So it's actually the 1 over 3 that is the important coefficient. Because here is now the main theorem. So we are carrying this course a lot about efficiency. And we have, putting the two lemmas together, we have the explicit formula for the cost. So the 1 over 3 in the leading term is most important, because in the LU factorization, one can show, and you can do this rather in a similar fashion as we did here. The other way would be to look into the textbook and to copy the formula from there. So what is important is that the LU factorization has the factor 2/3, whereas here we have the factor 1/3. And we know where the 1/3 comes from. The 1/3 comes from the sum of the I-squares. So in any, so just like complexity analysis, we only care about the leading terms and the polynomials in the dimension. But in this course, the constant coefficients also actually matter. So in the remaining slides, so actually the last slide, I would like to illustrate this. But first, one exercise, another follow-up exercise. You can actually show also the explicit cost of the LDL transpose factorization. You demonstrate, you derive the formulas from your solving of exercise 1. I think that exercise 1 started from a 3x3 matrix. So you generalize these formulas for an n-dimensional matrix. And you have one formula for the cost of the diagonal, and then another formula for the cost of the lower diagonal. So there are two parts in this exercise, worth 2 points. All right, so now comes almost my most important slide, computationally. Does this actually really matter? Well, here is a very simple experiment in an interactive Julia session at the terminal. I did this on a not so recent computer. The computer is 10 years old, but it has still a fast processor and also large memory. So and I would expect that for today's modern computers, having a 1000 by 1000 computer holding that in memory is not that difficult anymore. Now here I should also point out the semicolon. So the semicolons are actually now important. The semicolons suppress the output. We actually do not want to see the million elements, million random numbers. We are actually not interested in that. So we can time the LU factorization. So it took for, actually, this is a 10-year-old computer. It actually took less than a second, a third of a second. So the 1/3 is also there, but that's just a coincidence. And now there are some things that, here is the making of my my positive definite matrix. So this is different from what we did in the slides, because random lower triangular matrices are L-conditioned. And I hope we can explore this into a next computer project. But believe me, you should make for a 1000 by 1000 matrix. This is the way you take the output of an LU factorization. So random matrix is well conditioned, and the L that comes from the LU decomposition is also well conditioned. So this is an aside. So this is a very short slide, but it is actually an essential slide because there is also some non-trivial numerical analysis involved here, and that's the statement of the B here. Now, it's also, why does this still matter? So in the course, we run our algorithms on small inputs. That's because this is a course, but in many applications you work with large matrices. And here you see that we expect it to be 2 times faster, but we actually are almost 3 times faster. This means, intuitively, you could say Cholesky factorization is an algorithm that is simpler and easier to optimize. So these are all highly optimized codes that we are running. All right. So I should also say that we counted the floating point operations, but you can see here that the memory movements also matter. So we do a lot less allocation. We consume a lot less memory. So that's actually the reason for the more than double speed up that we expected. Okay, I'm running over time now. One last exercise. Repeat the previous experiment or the experiment on the previous slide on your computer. So I hope that all computers, so even if you do this on a laptop with less than 20 gigabyte main memory, that will also work. Give the main specifications of the computer. If you run this on the cloud, look up what computer runs this, so there might be a way to figure that out. And then report the timings for both the LU and the Cholesky factorization.